This is video 3D for the Year 12 Mathematical Methods course. In this video, we're going to be covering some example questions from Kinematics under the topic of Applications of Differential Calculus. The 4 questions we will be going through are now displayed on the screen, so I recommend that you attempt these questions before watching the rest of this video. Question 1. An object moves in a straight line with position from origin O given by s of t equals t squared take 7t plus 12 meters, where t is measured in seconds. Part A. Find expressions for the object's velocity and acceleration, drawing sign diagrams for each. So first of all, for the velocity function of this object, we know that the velocity is given by the first derivative of the displacement function. So because we have the displacement function s of t equals t squared take 7t plus 12, then we know that v of t must be equal to 2t take 7. Similarly, we know that the acceleration function a of t is given by the derivative of the velocity. So by taking the derivative of this function here, we get that the acceleration function is equal to 2. We now want to draw sign diagrams for both of these. So let's first of all draw the sign diagram for v of t. And the first thing we're going to do is set v of t equal to 0. So therefore we have 2t take 7 is equal to 0. So then by rearranging and solving for t, we get t is equal to 3.5. So if we set up this sign diagram for v of t, then we always have to start at 0. We can't have anything back here because we know that time, of course, has to be 0 or above. So this is our sign diagram for v of t. We have one 0 point at 3.5. So now we've got these two regions here that we now need to test for the velocity. For this first region here, we can test the velocity at t is equal to 1. Then v of 1 will be equal to -5. And we got that by just chucking t is equal to 1 into the velocity function here. Now this answer of -5 is of course less than 0, so we're going to pop a negative there. Then in the second region, we can test the velocity at time is equal to 4, in which case v of 4 is equal to 1, which is greater than 0, so we can put a plus here. So this here is our sign diagram for v of t. Now for the acceleration function, this one here is actually going to be relatively straightforward, mainly because there is no t value in the acceleration, it is just a fixed value of 2. So what that means is, if we want to draw out the sign diagram for a of t, then we just need to once again start at 0, t, and a of t. And we don't have any 0 points, so we're just going to leave this completely open. Now, purely because we know that the acceleration function is just this constant here of 2, it means that every acceleration value in here must be equal to 2, which of course is a positive value, so we're going to put a plus for the acceleration sign diagram. Part B. Find the initial conditions of the object and describe the motion at this instant. So, we know that when we are presented with the word initial, this essentially just means when time is equal to 0, because this is the very instant before the object starts its motion. So in order now to find the initial conditions of the object, we now need to find what s of 0 is, v of 0, and a of 0. So by substituting t is equal to 0 into the displacement function, we get 0 squared take 7 lots of 0 plus 12, which is equal to positive 12 meters. Substituting t is equal to 0 into the velocity function that we found in part A will give us 2 lots of 0 minus 7, which is equal to minus 7 meters per second. Now if we pay careful attention to the units here, we notice that we use meters because that's the units for the distance, and then seconds for that's the units of the time. And then finally, we know from part A that the acceleration function a of t is just equal to 2, and it has absolutely no time dependence, which means that in this case here, a of 0 will also be equal to 2 meters per second squared. So now that we have all these initial conditions of the object, we now need to use these to describe the motion of the object at this instant. So the best way that we can do that is first of all by analysing what each 3 of these answers actually mean. So if we first of all look at the initial displacement, that is equal to positive 12 meters, which means that initially the object is located 12 meters to the right of the origin. V of 0 is equal to negative 7 meters per second, which means that initially the object is moving left because it's negative with a speed of 7 meters per second. And then finally, because A of 0 is equal to positive 2 meters per second squared, we know then that it will be accelerating to the right because it's positive at a rate of 2 meters per second squared. So now let's combine all of this information into a nice final sentence. So we can say initially, the object is positioned 12 meters to the right of the origin, moving left with speed 7 meters per second, accelerating to the right with a rate of 2 meters per second squared. Now, what we notice about this final answer is that we have all the information that we found in these three calculations here. For the initial displacement of 12 meters, we are saying that it's positioned 12 meters to the right of the origin because it's a positive value. For the initial velocity of negative 7 meters per second, we're saying that it's moving left because the value is negative with a speed of 7. And then finally, with the initial acceleration equal to 2 meters per second squared, we're saying that it's accelerating to the right, because once again, it's a positive value, with a rate of 2 meters per second squared. So in each three of these descriptions, we have given both a direction and a size for each of the quantities. Part C. Find the position of the object when it changes directions. Alrighty, so we know that an object will reverse its direction when its velocity transitions from being positive to negative or negative to positive. Now, the best way that we can go about analyzing this is using the sign diagram that we found in Part A. Now, if you recall, the velocity sign diagram for Part A was as followed. We had a point here at 3.5. It was negative in this region and positive in this region. So from the sign diagram, we can see that the velocity transitions from negative to positive around the time of 3.5. So we can write this. Using the sign diagram, the object reverses directions at t is equal to 3.5. However, the question isn't asking us when the object reverses directions, it's asking us to find the position of the object when it changes directions. So we know that it changes directions when time is equal to 3.5, and we need to find the position of the object at this instant. How do we find the position? We substitute it back in to the displacement function. So we're going to find s of 3.5, and if you substitute this into the original displacement function, we get 3.5 squared, take 7 lots of 3.5 plus 12, which is equal to negative 0.25 meters. In any situation like this, I always recommend that you write your answer as a final sentence to give it some context. So in this case here, because it's negative 0.25, it means that we're going to be located to the left of the origin. So we're going to say the object reverses directions when the object is 0.25 meters to the left of the origin. Part D. Draw a motion diagram for the object. So whenever we're trying to draw a motion diagram, we need to know a few key important bits of information. Those bits of information include the initial displacement, the initial direction of motion, and any times and positions when it reverses directions. And the really good thing about this situation is that we've already found out all three of these bits of information. We found that initially the displacement was equal to 12 meters. We found that it was initially moving left, so that was part of our answer to part B. And we also found that it reversed directions at t is equal to 3.5 when its displacement, so s of 3.5, was equal to negative 0.25 meters. So what we can now do is construct a nice motion diagram capturing all this information here. So we can draw a horizontal axis, which represents the displacement at time t. We're going to indicate that the origin O is directly in the middle. Now, we've been told that initially it is positioned 12 meters to the right of the origin, so we can indicate that here. And the other key displacement that we have to consider is this negative 0.25, in which it reverses directions. So I'm going to just indicate that here just for now. However, we always start where the object starts. So we are saying that the object initially starts at a position of 12. So I'm going to write that t is equal to 0 because that's its initial displacement. And we then know that it starts to move left. And it continues to move left up until it hits this negative 0.25. And then it reverses directions. Now, because it only has one point where it reverses directions, we can then indicate that this object will then just continue moving to the right without any end. So in this particular case here, this point here is at t is equal to 3.5. And these are the only two important parts of information that we need to indicate in this case, where it starts and then where it reverses directions. Part E. During which time intervals is the object's speed increasing and decreasing? Alrighty, so whenever we're dealing with an object's speed increasing and decreasing, remember we need to consult the sign diagrams for the velocity and the acceleration. And if you recall what I mentioned in the corresponding theory video, my ultimate suggestion is, and this is because it's worked very well for me over the last few years, is to actually combine the two sign diagrams on top of each other, so then making the actual comparison of these times significantly easier to work with. So what I mean by that is we'll construct one total sign diagram. We know that time is always going to start at 0, so we can just indicate that here. But then on the top, this is where our velocity sign diagrams are going to go. And on the bottom, this is where our acceleration sign diagram is going to go. With our velocity sign diagram, we had a single 0 point at 3.5. To the left, it was negative, and to the right, it was positive. And then for the acceleration, there were no 0 points, and the entire thing was positive. Now, if you recall, an object's speed increases when the sign of the velocity and acceleration are the same. So in other words, when it's positive and positive or negative and negative, and the speed will decrease when the signs are opposite. So in other words, if velocity is positive and acceleration is negative, or vice versa. So let's start with the increasing speed. So the object's speed increases and if we consult the sign diagram, we can see that both the velocity and the acceleration are positive for this region over here. So in other words, when time is greater than 3.5, so we can write that here. So the object speed increases for t is greater than 3.5. Conversely, the object speed will decrease and again, if we consult the sign diagram, we can see that the velocity function is negative, whereas the acceleration function is positive. So because they're opposite signs, the speed will decrease. So in other words, this is between 0 and 3.5. So we can say that the object's speed decreases for time being between 0 and 3.5. Question 2. An electron moves in a straight line with position from origin O given by s of t equals 15t, take t cubed, take 6t squared plus 6 centimeters, where t is measured in seconds. Part A. Find expressions for the electron's velocity and acceleration, drawing sign diagrams for each. So we know that the velocity function v of t is equal to the first derivative of the displacement function s of t. And just to quickly recap, s of t that we are given is 15t take t cubed take 6t squared plus 6. So therefore, by taking the derivative of this displacement function, we get 15 take 3t squared take 12t. Further, we know that the acceleration function a of t is given by the derivative of the velocity function. So, by taking the derivative of this function up here, we get negative 6t take 12. So now that we have both of these expressions here, we're now going to work on actually drawing up the sign diagrams. So the first thing I'm going to do is work on the velocity sign diagram, and what we can do from here is set this expression equal to 0. So we've got 15 take 3t squared take 12t is equal to 0. And in order to solve this, I'm just going to come over to my graphics calculator and use the equation solver. So coming down to this menu here, then polynomial of degree 2, because we're working with a quadratic, and our coefficients are -3, -12, and +15. So by solving this, we get time values of -5 and +1. So let's write these out here. So t is equal to -5 and +1. However, we know that t must be greater than or equal to 0, so the only solution that we can take in this case is when t is equal to 1. So now by constructing a sign diagram for this, we of course are going to start at 0 because time cannot be less than 0. This is going to be for time and our velocity function. We've only got one time for which the velocity is equal to 0, which is at 1, so we'll indicate this here. So now we've got these two regions here that we need to test out the velocity function for. For this first region here, we can test out the velocity at t is equal to 0.5, in which case v of 0.5 is equal to 8.25, and that's just by substituting 0.5 back into the original velocity function. And because this is greater than 0, we're going to put a plus here. And then for the second region, we can test out the velocity at t is equal to 2, in which case v of 2 is equal to -21, which is less than 0, so we'll pop a minus sign there. So this here is our sign diagram for the velocity function. We'll now approach the acceleration function very similarly. First thing that we're going to do is set the acceleration function equal to 0, in which case we get -6t take 12 is equal to 0. And if we solve this equation, then we find that t is equal to -2, but we know that t must be greater than or equal to 0, so we have no times in which the acceleration is equal to 0. So now if we use this fact to construct a sign diagram for the acceleration, then we get the following. T and a of t, and once again we're going to start our sign diagram at 0. And in this case, because there are no times in which the acceleration is equal to 0, we're just going to keep this entire region open, but now we need to test to see whether the acceleration is positive or negative in this entire interval here. The way that we can do that is by testing out at a value. So we can just test it out at t is equal to 1, in which case the acceleration evaluated at 1 is equal to -18, which is less than 0, so we're going to pop a minus in there. So that there is our sign diagram for the acceleration function. Part B. Find the initial conditions of the electron and describe the motion at this instant. So just as a quick reminder, whenever we hear the word initial, this means when time or t is equal to 0. So in order to find the initial conditions, we need to find what s of 0 is, we need to find v of 0, and we need to find a of 0. So by substituting t is equal to 0 into our displacement function, then we get 15 lots of 0, take 0 cubed, take 6 lots of 0 squared plus 6, which is equal to +6 centimeters. If we substitute t is equal to 0 into the velocity function that we found in part A, then we get 15 take 3 lots of 0 squared take 12 lots of 0, which is equal to +15 centimeters per second. And once again, you'll notice that with our velocity units, we take the centimeters because that's the units for our distance, and then we take seconds since that's the units for our time. And then finally, a of 0, by substituting t is equal to 0 into the acceleration function from part A, we get -6 lots of 0 take 12, which is equal to -12 centimeters per second squared. So before we write our answer as a nice final sentence, let's analyze what each three of these quantities actually mean. So our initial displacement is 6 centimeters, which means that initially the electron is positioned 6 centimeters to the right of the origin. Our initial velocity is 15 centimeters per second, which means that initially the electron is moving to the right with a speed of 15 centimeters per second. And finally, our initial acceleration is negative 12 centimeters per second squared, which means initially the electron is accelerating to the left at a rate of 12 centimeters per second squared. So now let's write all of that as a nice final sentence. So we can write initially the electron is positioned 6 centimeters to the right of the origin, moving right with speed 15 centimeters per second, accelerating to the left at a rate of 12 centimeters per second squared. And what you'll notice is, in this sentence, we've gotten all the information that we presented in our previous analysis. So for the initial displacement of 6 centimeters, then we've got the 6 centimeters and the fact that it is positioned to the right of the origin because the quantity is positive. For the initial velocity of 15 centimeters per second, we're saying that it's moving right because the quantity is positive and the speed of 15 centimeters per second. And finally, the initial acceleration of negative 12 centimeters per second squared, we're saying that it's accelerating to the left because the quantity is negative at a rate of 12 meters per second squared. Part C. Find the position of the electron when it changes directions. So, we know that the electron will change directions when the sign of its velocity switches from negative to positive or positive to negative. So let's quickly write this down. So the electron will reverse directions when its velocity changes sign. And the easiest way that we can analyze this is by using the exact same sign diagram for velocity that we constructed in part A. So just coming back to that sign diagram, we had this here. So we found that v of t was equal to 0 at 1, and that this region here was positive and this region here was negative. So just by looking at the sign diagram, we can see that velocity transitions from positive to negative around the t is equal to 1 mark. So what that means is, from the sign diagram, the electron reverses directions at t is equal to 1. However, the question is not asking us to find the time in which the electron changes directions, it's asking for the position. So we know that it reverses directions at t is equal to 1, and so we can find its position by substituting this into the displacement function. So in other words, s of 1 is equal to 15 lots of 1, take 1 cubed, take 6 lots of 1 squared, plus 6, and by calculating all this, we get an answer of positive 14. So now let's actually write this answer as a full sentence. So we can write, when the electron reverses directions, it is positioned 14 centimeters to the right of the origin. And of course we know it's positioned to the right because this quantity here is positive. Part D. Draw a motion diagram for the electron. So we know that whenever we're going to be drawing a motion diagram for a particular scenario, we need to know 3 important bits of information. We need to know the initial displacement, the initial direction of motion, and when and where it reverses directions. So, from part A, we know that its initial displacement, s of 0, is equal to 6 centimeters. In other words, it is positioned 6 centimeters to the right of the origin. Its initial direction of motion is right, and we know that because the initial velocity was positive, so it must be moving to the right. And then, most recently, from part C, we found that it reverses directions at t is equal to 1, and we found that at this time it is positioned 14 centimeters to the right of the origin. So now, if we construct our motion diagram, we have a straight horizontal line displaying the displacement. We'll slap the origin right there in the center, and our two key points along this axis here are going to be the initial displacement, which is at 6 centimeters to the right, so I can pop that one there, and the point at which it reverses directions, which is at 14 centimeters to the right. So let's start where it initially starts, which is at this 6 here. I'm going to indicate that this is time is equal to 0. Then we know that initially the electron is moving to the right. So it continues this way until it hits this 14, and then it reverses directions. So I'm going to indicate that this point here is at t is equal to 1, which is what we found here. And now, because we know that the electron only reverses directions at this single point, it means we can indicate that the electron is just going to keep moving to the left without any intention of stopping. Part E. During which time intervals is the object's velocity increasing? Now, this is a question which you have to make sure that you're very, very careful with, because in this particular case, a lot of people are going to confuse this with the next question, which is all about when the speed is changing. So in this particular case here, we're being asked when the velocity is increasing. And the really nice thing about velocity is that we know that v of t, the velocity, increases when the acceleration function is positive. So you don't have to do any fancy comparisons with the acceleration and the velocity. We know very strictly that the velocity will increase when the acceleration is positive. Now, the best way that we can go about analyzing this is by using the sign diagram for the acceleration that we found in part A. If we recall the acceleration function, then we found that the acceleration function is always negative. So because the acceleration function is never positive, it means that the velocity, v of t, never increases. And finally, part F. During which time intervals is the object speed decreasing? Now, this one here, we do have to do a fancy comparison between the velocity and the acceleration, because we're being asked when the speed is decreasing, in which case you have to make this comparison. So we know that an object's speed will decrease when its velocity and its acceleration have opposite signs. In other words, when one of them is positive and the other one is negative. The easiest way that we can go about this is by looking at the two sign diagrams for v of t and a of t and compare the two of them. So again, my ultimate suggestion is to construct one big sign diagram where the velocity sign diagram is on the top and the acceleration is on the bottom. If we recall what the velocity sign diagram looks like, we have a 0 point when t is equal to 1. This region here is positive, this region here is negative, and then the acceleration sign diagram is negative consistently. So in this particular question, we're looking very strictly at when the speed is decreasing. And if we have a look at the sign diagram, we can see that the velocity and the acceleration have opposite signs in this region here. Between 0 and 1, when the velocity is positive, but then the acceleration is negative. So we can therefore say that the speed will decrease when time is between 0 and 1. Question 3. A skydiver falls directly towards the ground with displacement in meters from a plane given by function s of t equals 30t plus 400 e to the power of negative t over 15, where t is the time in seconds since the skydiver jumps out of the plane. Part A. Find the velocity and acceleration functions of the skydiver. So we of course know that the velocity function v of t is given by the derivative of the displacement function s of t. Just as a quick reminder, our displacement function in this case is 30t plus 400 e to the power of negative t over 15. So therefore the derivative function of this will be 30 plus 400. Then we're going to multiply the front by negative 1 over 15. Then e to the power of negative t over 15. If we simplify this a little bit, we get an answer of 30 take 80 over 3 e to the power of negative t over 15. And then further, we know that the acceleration function a of t is given by the derivative of the velocity function. So by taking the derivative of this function here, we get the following. Negative 80 over 3, then we're going to multiply the front again by negative 1 over 15, then e to the power of negative t over 15, and then by simplifying this a little bit, we get 16 over 9 e to the power of negative t over 15. So they're our velocity and acceleration functions. Part B. Find the initial position, velocity, and acceleration of the skydiver. Now, before we even get into any calculations to do with this question, we do have to understand a little bit more about the directional situation of this question. Because 99% of the time in kinematics, your directions will be left and right, where right is given by a positive value and left is given by a negative value. But if you imagine what's going on here, we've got the ground level here, we've got a skydiver which is jumping out of a plane, and the skydiver is going to be moving down towards the ground. Now, if we read the question very carefully, it says the following. With displacement from a plane given by the function s of t equals blah blah blah. So what that means is that the displacement is a measure of how far away the skydiver is from the plane as it falls towards the ground, which means that the downwards direction is going to be positive and the upwards direction therefore must be negative. So whenever you're in a situation like this where the motion is not left and right, you have to first of all make sure you understand which direction we're giving the positive values to and which direction we're giving the negative values to. And we'll see how this plays quite a big effect in what we're about to do here. So coming back to the original question, find the initial position, velocity, and acceleration. We know that the word initial essentially just means when t is equal to 0. So if we want to find the initial position, velocity, and acceleration, this means that we need to find s of 0, v of 0, and a of 0. So by substituting t is equal to 0 into our original displacement function, we have 30 lots of 0 plus 400 e to the power of negative 0 over 15, which is equal to 400 meters. V of 0, if we pop in 0 into our velocity function from part A, we get 30 take 80 over 3, e to the power of negative 0 over 15. And by rounding this answer to a few decimal places, we get about 3.33 meters per second. The units in this case you'll notice are meters because that's the displacement units, and then seconds for that is the time units. And then finally, by substituting t is equal to 0 into our acceleration function from part A, we get 16 over 9 e to the power of negative 0 over 15. And again, just rounding this to a few decimal places, we get 1.78 meters per second squared. Now, even though the question isn't actually asking us to describe what these three values mean, I think it's a good idea just for what we're about to do to get a good understanding as to what these three values mean in the context of the question. So we're first of all saying that the initial displacement is 400, which means that when the skydiver leaves the plane, they are 400 meters above the ground. In other words, their entire journey here is going to be 400 meters because that is how far they initially start above the ground. Then we are being told that the initial velocity is 3.33 meters per second, which means that as soon as the skydiver jumps out of the plane, they are traveling at a speed of 3.33 meters per second. And we notice that this value here is positive, which makes sense since the downwards direction we've defined as positive, and we expect the skydiver, once they've jumped out of the plane, to travel downwards. This answer here would be quite weird if you got a negative answer, because then what that would indicate is that the skydiver is traveling upwards, which of course makes absolutely zero sense. And then finally, the acceleration is positive 1.78 meters per second squared. Notice once again that this value here is positive, which means that the acceleration is also directed downwards. And this once again makes sense because in the context of this question, the reason why the skydiver will be accelerating is because of gravity, which is physically pulling the skydiver down towards the Earth. So we expect the acceleration to act downwards because that's the way that gravity also acts. Part C. Discuss the skydiver's velocity as t approaches infinity. Discuss a possible explanation for this. So just as a quick recap from Part A, our velocity function was 30 take 80 over 3 e to the power of negative t over 15. And we want to discuss this as t approaches infinity. So the easiest way to analyze what's going on here is I'm first of all going to take out this little section here and analyze what happens to this one factor as t approaches infinity. Now what I'm going to do here, just to make things a little bit easier for us, I'm going to come up to our graphics calculator and I'm going to pop this expression in. So I've got negative something over 15, and because we want to analyze this as t approaches infinity, it means that we're just going to put a really big number here. Now my suggestion is put in a really big number. Pop as many zeros here as you want, execute that, and what we can say from here is that as t approaches infinity, e to the power of negative t over 15 is going to approach 0. So therefore what we can say from here, therefore v of t will approach 30 minus 80 over 3. Then we're saying that this thing here is going to approach 0. So we can pop 0 in there, which is equal to 30 minus 0, which is equal to 30 meters per second. So what this essentially here means is that as time progresses, then we expect the skydiver's velocity to eventually stabilize to 30 meters per second. Now let's think about why this might be the case, because the question's actually asking us to provide a possible explanation for this. Now this explanation might be a little bit more intuitive for the physics students as well, but let's have a good think as to what's actually happening as the skydiver approaches the ground. So of course we know that the reason why the skydiver is approaching the ground is because gravity is pulling them downwards. However, what you know about a person that is falling towards the ground is that they're also going to be facing an opposition force. This opposition force, which is going to be pushing them back up, is air resistance. So you can imagine this, you're falling from a certain height, or if you drop a ball or whatever, no matter what that object is or how far up above the ground they are falling from, air resistance will be opposing the force of gravity. It's physically going to be pushing them back upwards. And the interesting thing about air resistance is that the faster you travel, the more effective air resistance is. So what you can imagine is gravity is going to be pulling this skydiver further and further down, and it's going to be picking up speed. But because it's picking up speed, the air resistance is also going to be pushing it further and further up. Eventually what happens is the force in which the person's falling with, so the force due to gravity, is going to balance with the air resistive force. So because of that, even though the person's still falling, it's not going to pick up any more speed because the air resistance will be pushing them back up so much that it can't take on any more speed. And the way that we actually explain this in the real world is we refer to this as terminal velocity. So if you've ever heard of terminal velocity before, this is the greatest speed in which an object can fall towards the Earth, in which gravity and air resistance essentially balance each other out. So the way that we can explain this one is that this is terminal velocity, or in other words, i.e. when air resistance matches gravitational force. That is, the skydiver will not further increase their speed. Part D. Find the exact time such that the skydiver is moving with speed 20 meters per second. So in this case here, we want to set the velocity function v of t equal to 20 meters per second. Now, if you recall from our answer from part A, we found that the velocity function v of t was equal to 30 minus 80 over 3 e to the power of negative t over 15. So now we want to set this entire function here equal to 20 and solve for the exact value of t. So recall that when you were being asked to solve for this value here exactly, it means that we can't give it in a decimal form, we have to give it in its most exact form. Now because this equation here involves an exponential, it means that your answer will involve some form of a logarithm. But let's just go about rearranging this and we'll see what we get. First thing I'm going to do is subtract the 30 from both sides. So then I get negative 80 over 3. Then e to the power of negative t over 15 is equal to negative 10. Then I'm going to divide both sides by negative 80 over 3. And that will then result in e to the power of negative t over 15 is equal to 3 over 8. I'm now going to take the natural logarithm ln of both sides. So I can write ln e to the power of negative t over 15 is equal to ln of 3 over 8. ln of e to the power of negative t over 15 is just going to be negative t over 15. Then this right hand side, because ln 3 over 8 is not a particularly nice answer as a decimal, we'll just leave it in this exact form here. Then multiplying both sides by negative 15, we'll get as an answer of t is equal to negative 15, then ln of 3 over 8. Now, the easiest way in which you can check to see if this answer is correct is by substituting this value here back into your calculator with the original velocity function, and to see then if our answer is 20 meters per second. So if we come back to our graphics calculator, our velocity function was 30, take 80 over 3, then e to the power of negative t over 15. We've just found out that our time value is negative 15 ln of 3 divided by 8. So I'm going to pop that value in there. And our then overall answer is equal to 20, which is exactly what we wanted to get. So we know that this answer here must be correct. Part E. Show that v of t is greater than 0 for all t. What is the significance of this result? Alrighty, now whenever you're trying to show that the velocity and acceleration function are either greater than 0 or less than 0 or whatever, my ultimate suggestion is to use a sign diagram. There are a few different ways they can go about it, such as a graphical method or through algebraic purposes. However, in situations like this, I've always found that a sign diagram is significantly easier to use, and it requires a lot less work in the end, which can be quite helpful, especially in a test or exam. So I'll show you this method and see if you like it or not. So we want to show that v of t is always greater than 0, or in other words, that v of t is always going to be a positive value. Now, if you recall from our answer from part A, v of t is equal to 30, take 80 over 3, e to the power of negative t over 15. And we are now going to construct a sign diagram for this. So I'm just going to draw this empty sign diagram over here. We know that time has to be a non-negative value, so it's going to start at 0. So this is t and then v of t. So as per our normal protocol when doing a sign diagram, I'm first of all going to find out when this entire function here is equal to 0, and then we're going to put that on the sign diagram. So let's write v of t is equal to 0, so therefore 30 take 80 over 3 e to the power of negative t over 15 is equal to 0. If I subtract the 30 from both sides, I get negative 80 over 3 e to the power of negative t over 15 is equal to negative 30. Then dividing both sides by negative 80 over 3, we get e to the power of negative t over 15 is equal to 9 over 8. Taking the ln of both sides, we get ln of e to the power of negative t over 15 is equal to ln 9 over 8. This left-hand side will simplify down to negative t over 15 is equal to ln 9 over 8. So then rearranging this and solving for t, we get t is equal to negative 15 ln 9 over 8. And if you pop this into your calculator, then you get a rough answer of negative 1.767. However, we know that time strictly has to be a non-negative value, which means that we cannot take this value when we are considering our sign diagram. So that means that when we come back to our sign diagram up here, we have got no points in which v of t is equal to 0, so it means that we can just keep this open as one big interval. So then, as you normally would whenever you're dealing with a sign diagram, we're now going to test out the velocity function at some point in this region here to see if it's a positive answer or a negative answer. So the easiest way that you can think about doing this is we'll just substitute t is equal to 1. So then v of 1, if you chuck 1 into your velocity function, is equal to 5.05, which is greater than 0, so I can pop a positive in that region there. So what this means is that whenever t is greater than 0, then the velocity function will always be positive. So in other words, therefore, v of t is greater than 0 for all t greater than 0, which is exactly what we wanted to show. So now what we need to do is we need to discuss the significance of this result. Coming back to the original context of a problem, we defined the upwards direction as negative and then the downwards direction as positive. So because v of t is always positive, it means that the skydiver will always be moving downwards, since that is the positive direction. And again, just from a realistic standpoint, this makes a whole lot of sense, because when a person is jumping out of a plane and falling towards the earth, we don't suddenly expect them to travel upwards, because that's not how gravity works. So the fact that v of t is always positive means that the skydiver is always moving downwards, which from a realistic perspective makes sense. So therefore, the skydiver is always moving downwards. That is, towards the ground. Part F. Show that a of t is greater than 0 for all t. What is the significance of this result? So, very similar to our last question, we are now aiming to show that the acceleration this time is always positive for all values of t. What we're going to do here is we'll approach this very similarly to how we did the velocity function, in that we are going to use a sign diagram. Now, if you recall from our answer from part A, our acceleration function that we found was 16 over 9, e to the power of negative t over 15. And if we construct an empty sign diagram from here, we have t being strictly greater than or equal to 0, and this is for our acceleration function. So what we're going to do here is first of all set the acceleration function equal to 0, and then solve for what values of t satisfies that. So if we say a of t is equal to 0, then 16 over 9, e to the power of negative t over 15 is equal to 0. Dividing both sides by 16 over 9 first of all, we get e to the power of negative t over 15 is equal to 0. Taking the ln of both sides, we get ln of e to the power of negative t over 15 is equal to ln 0. Now, the interesting thing about this equation here is that ln of 0, and you can even show this on your calculator, is undefined. So because this thing here is undefined, it means that there is no value of t which can satisfy this entire equation. So what that means is that a of t will never be equal to 0. So which means, coming back to our sign diagram, we can just keep this entire interval open without any 0 points. So now, as usual, we will test out the value of the acceleration function for a time in this region here, and test whether it's a positive answer or a negative answer. So the easiest way that you can go about doing this is to substitute t is equal to 1. So then a of 1 is equal to 16 over 9, e to the power of negative 1 over 15, and if you chuck that into your calculator, you get an answer of roughly 1.663, which is greater than 0, so we're going to pop a positive in there. So because we only have one interval, which is from when t is greater than or equal to 0, and this entire interval we're saying that acceleration is positive, we're going to say, therefore, a of t is greater than 0 for all t being greater than 0, which is exactly what we wanted to show. So now we need to think about what the significance of this result actually is, and we're going to have to go into a little bit more depth here than we did with the last one, because once again we defined the downwards direction as positive, which means that the acceleration direction is always going to be directed downwards. And coming back to the actual context of this problem, that makes sense, since the acceleration of the skydiver is being caused by gravity, and because gravity always acts downwards, we expect the acceleration to always act downwards as well. So that's the first point that we can write here. The fact that, therefore, the skydiver will always be accelerating downwards. However, the other thing that we can definitely make mention of in this case is what's happening to the skydiver's speed. Because we found in the previous part that v of t is always greater than 0, and we've just found here that a of t will always also be greater than 0. So because for all time intervals, v of t and a of t have the exact same sign, it means that the skydiver's speed will always be increasing. And again, the context of a problem, this makes a lot of sense. You don't suddenly expect the skydiver's speed to decrease when they are literally falling towards the ground. We expect that speed to be continuously increasing. So this is the other thing that we can write here. The skydiver's speed is always increasing. Question 4. An electron oscillates back and forth in a horizontal antenna. The electron's horizontal displacement relative to the center of the antenna is given by S of t equals 1/4 sine of t over 3 meters, where t is measured in seconds. Part A. Describe the position of the electron after 10 seconds. So in order to determine the position of the electron after 10 seconds, we have to get the displacement function and substitute t is equal to 10 into that function. Doing so will get us 1/4 sine of then time, which is 10 divided by 3. And if you chuck this into your calculator, making sure that your calculator is set to radians and not degrees, then you get an approximate answer of negative 0.0476 meters. In other words, the electron is 0.0476 meters to the left of the antenna's center. So because in this case we've got left and right motion, anything to the right of the antenna's center will be positive and anything to the left will be negative. Part B. Find the velocity and acceleration functions. So we of course know that the velocity function v of t is given by the first derivative of the displacement function. So by taking the derivative of s of t equals 1/4 sine of t over 3, then we get 1/4, then the derivative of the inside, which is 1/3 cos of t over 3, which is equal to 1/12 of cos t over 3. Then we know that our acceleration function, a of t, is given by the first derivative of the velocity function. So taking the derivative of this function here, we get negative 1/36 sine of t over 3. Part C. Show that the electron's speed is maximized when it moves past the antenna's center point. Alrighty, so now we're going to be looking at maximizing the speed. Now, if we recall, we know that the speed of an object is given by the size or the magnitude of the velocity function v of t at that particular time. So what that means is we want to maximize the absolute value or the size of v of t. Now the way that we're going to do this is we're going to consider when v of t is maximized and minimized. And we know that this is going to occur when the velocity function's derivative is equal to 0. In other words, when v dash of t is equal to 0, but we know that v dash of t is just the acceleration function. So in other words, we want this to be a of t is equal to 0. From part B, we found that the acceleration function was negative 1/36 sine of t over 3. And we're going to set this equal to 0. Now, by dividing both sides by negative 1/36, from this we get that sine of t over 3 must be equal to 0. Now, instead of solving for the exact values of t that satisfies this equation, I'm first of all just going to write this. So we know that the velocity, so v of t, is maximized or minimized when sine of t over 3 is equal to 0. Now, if you read the question very carefully, it's asking us to show that the electron's speed is maximized when it moves past the antenna's center point. So because of the wording of that question, it indicates to me that we're going to have to use something to do with the displacement function. And if we come back to the displacement function, which is s of t is equal to 1/4 of sine of t over 3, we know that sine of t over 3 is going to equal to 0, so let's set this part here equal to 0. Doing that, we get s of t is equal to 1/4 multiplied by 0, which is of course just 0 meters. So let's have a look at what this result actually means. We know that v of t is maximized or minimized when this equation here is satisfied. However, what this here means for the displacement function is that when this is satisfied, the displacement is equal to 0. So what this means is that v of t is maximized or minimized when s of t is equal to 0, or in other words, when the electron moves past the antenna's center. Because we know that the displacement function is relative to the center of the antenna, so when the displacement is equal to 0, it means that it is at the center of the antenna. But we're not quite there yet with the final answer, because we've showed that v of t is maximized or minimized when s of t is equal to 0, but we're looking for the speed. However, we know that the speed is equal to the absolute value of the velocity function, so we know that the speed is maximized when v of t is maximized or minimized. And let's quickly go through why this is. So let's say we know that v of t has a maximum of 5 and a minimum of -5. Well, what we can see in both of these cases is that the speed is 5 in this one, and the speed will be 5 in this one here as well. So because of the symmetrical nature of the trig function, we know that speed is going to be maximized when the velocity function is either at its highest or at its lowest value. So therefore, combining all this information, we can therefore say that the speed is maximized when the electron moves past the center. Part D. Show that the acceleration function a of t is equal to -1/9 multiplied by s of t. Explain the significance of this result. So, we wish to show that the acceleration function a of t is equal to -1/9 of the displacement function s of t. Now, we have expressions for both the acceleration and the displacement function, so we know that the displacement function s of t is 1/4 sine of t over 3, and from our answer from B, we found that the acceleration function a of t is equal to -1/36 sine of t over 3. So what I'm going to do with this acceleration function is I'm going to split up this leading term. So I'm going to split this up into -1/9 multiplied by 1/4 sine of t over 3. And we can see here that the equation hasn't actually changed because we've still got the sine of t over 3 here, and this -1/36 is now just split up into those two factors there. However, the really nice thing about this situation is we can see that this entire thing here is just the displacement function. So we can rewrite this then as a of t is equal to -1/9 multiplied by the displacement function s of t. Now, let's explain the significance of this result, because what this result here tells us is that the acceleration function will always be the opposite sign than the displacement function. If a displacement function is positive, then the acceleration function will be negative. If a displacement function is negative, then the acceleration function will be positive. Now let's think about what this means. Imagine we've got our antenna here, with this here being the center, then what this here means is that if the electron is located at some point to the right of the center, so in other words, when s of t is greater than 0, it means that the acceleration is going to be directed towards the left, so it's going to be pulled in this direction. Conversely, if we've got the electron over here, so when s of t is less than 0, because it's to the left of the center point, it means that the acceleration will be positive, which means that it will be pulling in this direction here. Now this really makes sense, because what we're saying is that the antenna has a fixed length, and that the electron is going to be bouncing back and forth, back and forth, back and forth. The only way that that can happen is if it's on this side here, it's then going to reverse directions to this side, and if it's on this side here, it eventually has to reverse directions to that side there. So now let's write this as a nice final answer. So what we can say here is that the electron's acceleration will always be the opposite sign to its displacement. Therefore, when the electron is located to the right of the center, it is accelerating left, and when the electron is located to the left of the center, it is accelerating right.